you ever looked at a crystal structure like this or seen something in class, it's very deceptive because of the additions they've made to indicate a bond. And really a bond is not actual structure, it's an interaction between electrons and protons, between neighboring atoms or ions. And so when you look at a structure like this, there's a lot of deception in that. And so when you go into higher levels and learn about unit cells and density calculations and body center cubic and face center cubic, some of that can be disrupted by that. So what I've tried to do is try to build some models that are a little more appropriate, where instead of these artificial structures holding together, we can see more of just contact between what these would look like if we could have atoms or ions appear as a sphere. And I want to walk you through what some of the different analysis we could do on unit cells such as face center cubic, body center cubic. So face center cubic, if we were to try and draw, we would draw our cube like that. So in a face center cubic, what you're going to have is you're going to have one atom in each corner of the cube. 1, 2, 3, 4, 5, 6, 7, 8. Right. So you have these 8 atoms. Here's 1, 2, 3, 4, 5, can't see 6 back here, 7, and 8. Right? Yep. But then what you have in addition to that is that each face of the cube, you also have an additional one. So you have one here on this front side, one here, one on top, one on this back one on this back one, and one on the bottom. And when you look at how that's arranged in a cube, it can again be deceptive because you're leaving these gaps between things. So this is what this looks like with a space-filling model. And here we can see a few things. One is we can look at the connectivity. So which atoms are actually touching. And it's tricky to even decipher that on a picture like this. But what we find is that this atom here on the corner and this atom here on the bottom corner are not in contact with one another. There's a gap between them. Right? So I have a model built here that's a little rough, but what we're saying is that there's a gap between these two atoms. And so the contact actually is going to run across a diagonal of the face from here to here to here. So the way I would draw that on our structure here is I would say that there's contact from this point to this point across this diagonal. Now if I look at my cube, what I'm drawing there is I'm drawing a diagonal across the face of the cube. So what we're going to see later is that that's going to allow us to get information about the size of the cube based on the size of the atoms involved in the ions. Now, over here we have body center cubic. In a body center cubic cube, you have a really simple arrangement. You have a cube, as we just saw, and then you have one atom at each corner. So you have your 8 atoms there. And then you have one that's in the middle of the cube. Now the contact there is a little trickier. You can see here there's a gap here between the edges. And then also, and then if we go from the diagonal, you're going in towards the center and then back out to get to here. So unlike over here where we have this diagonal where there's constant contact in between, this one, when we have our constant contact, it kind of is interrupted. And so to get a full idea of where there's connectivity that can give us useful information, we actually start on one side. I'm going to start on this atom here at its center, so on this back one, and then draw that through the center to the front side. So actually a diagonal across the entire cube. So from here, all the way through the center to the opposite corner of the cube is where we have this contact. And so we can have the radius of this, plus the diameter of the center one, plus the radius of this corner, where we have full contact. So what we want to do then is show you kind of what you can do with that and how you can use that to your advantage. Now, if you want to see this a little more visually, and keep in mind that these patterns we're showing you here are greatly simplified down from what they would look as we extend out in 3 dimensions. So as we make these crystals larger and longer in the X, Y, and Z direction, you're going to see some more difficulty in kind of identifying the patterns. So for example, if we look at our face center cubic model, as we extend this out, you're going to find that it's actually kind of complicated to see what's going on in it. But a good way to kind of get a vision of that is to start with a larger lattice. And something simple you can do for that is to just stack tennis balls on top of one another. And what you're going to find when you do that, and I'll show you in a second with the tennis balls, is that when you start with your initial layer and then put a second layer on top of that into where some of the holes are arranged, you'll find two different options. One is you can repeat the first layer. So you can go from an A layer to a B layer to again back to the A layer. So in other words, we would take this entire bottom layer here and recreate it exactly on top of where it is. Alternatively, there's another way you can arrange where you do the first layer, the second layer, and then there's a third layer that's different from the initial one. This is where we get our face-centered cubic model from. This is a hexagonal close pack that we're not going to really look at in this video, but this is our face-centered cubic pattern, and very, very difficult to see when you do that arrangement. So a good way to make this kind of cubic system and to get an idea of, or appreciation that it goes beyond just one of these simple cubic structures like this, is to just get a whole bunch of tennis balls. And so if we start with a simple cubic sodium chloride style structure, we have something like this. This is a very inefficient way to pack your material. So by shifting the center row up a little bit, we can compress those so that there's less wasted space in between all of them. Okay, so this is usually how we start our structures. Then from there, just start putting tennis balls in. And what you'll find is there's a particular way they fit. And if you start to add more and more, what you'll find is that there's two different ways to pack these, where you kind of have what we'll call an A layer underneath, and then a different layer, B layer, that doesn't fit above directly. So we could always stack these directly on top, but if we put them here instead, we'll find that they have a better fit and that they'll take up more of the space, so they'll be more densely packed. Now from there, what you'll find is that there are two different spots we can put the next tennis ball. When you look here, you're going to see a tennis ball underneath, directly underneath. So if I put a ball here, what that's doing then is it's repeating this A layer. So we're going from A to B to A again. And as we start to continue out more tennis balls in all the directions, we're going to have an AB, AB, AB layer. Alternatively, this spot right here, we have a hole. So I don't know if we can kind of, I don't know how well you can see that there. Let's see if I can scoop this. So right down there, if you stare down, you'll see that there's a gap in between. This one is directly on top of a tennis ball. This one is directly on a hole. So what that means is when I put the tennis ball here, now I've started a brand new layer. This is A, B, and now C. And then when I do a new layer on top of that, I'll get back to the layer A. This way is what's called the face-centered cubic. And so what I've done here is I've arranged these in a structure that's just like this one over here, except I've done it in a little different fashion. Now this doesn't look like this to us, and part of that's because of the contact between the tennis balls is a little different than this, but we have this same style structure where we have a cube, and then in between each face there's one more on each face of the cube. Now the packing on this might not work because all the tennis balls are the same size, but that's the arrangement we're setting up. And you can't see that because the angle that you'd have to look at it and the geometry are very difficult to kind of understand. But we just made this using the tennis balls. Here's another angle on our face-centered cubic. What I want you to understand is that one of the key things we're going to talk about here is this face right here, these four green and the one white one here in the middle, that the contact on these goes from the diagonal piece to the center piece to the other diagonal. And so if all four of these were the same size, we would have the radius of this, the diameter of this, and the radius of this would be our diagonal length across this length of my cube. Okay. Now again, when we were looking at the tennis balls earlier, we were looking at a view that's different. We were looking more at a view that's like this, and you can see that it's the 3 underneath the 1 stacked on top is kind of the view that we were seeing. Here it's a lot more cubic in nature, and it's easier for us to kind of understand this as opposed to this kind of giant mess of tennis balls. It's really hard to differentiate what the different patterns are. This is much easier to work with in a unit cell for analysis purposes. Now for this one again, our contact is from here to here to here. These two are not touching. So there's a gap between these two. I can't just take 2 times the radius of this and say that that's the length of my unit cell. I have to figure it out by the ones that are touching. And then lastly, here's our face-centered cubic. Now this one doesn't fall into the same jurisdiction as the A, B, C layers as the other ones. We would get hexagonal close packing. And you can also note that this one is not built as nicely as the other one because this one just doesn't fit very well. And so the size of the atoms or ions in these is really important in determining which way these are going to form crystal structures. In this one though, the question is, well, what's touching in this one? So this one we have a white one in the center, and then we have our 8 cube corners here. And so the contact is actually from this one through the centerpiece all the way over to the opposite diagonal. So these two are not touching, these two are not touching. In fact, none of the green ones are touching. It's that the green one attaches to the white and then the opposite corner. So these two are the two where there's contact through the one that's in the middle of that. And that's how we're going to have to do our calculations. So we know that the radius of this plus the diameter of the center plus the radius of this is going to be equal to this kind of diagonal across the cube. And then from there we're going to be able to figure out the side length by doing the side length here and then the diagonal side length in one kind of big right triangle. So if I'm connecting these two, we're going to look at it as kind of a right triangle where we have our hypotenuse running down through the cube, and then we have the diagonal from here to here, and then lastly the length from here to here. So a little more challenging to see. We'll go ahead and draw it on the board. Okay, we're back on body center cubic. So let's go ahead and get a cube drawn here. Okay, so for a body center cubic, we're going to have 8 atoms, 1 at each corner. There's our 8. And then we're going to have one more that's in the center of the cube. So we'll draw just a really big one there. We won't worry about overlap. Now, one of the key questions here is how can we relate the radius of these atoms to the length of the side of the cube? And that's critical information because often we will know one of these two things, either from density or from some kind of other external information where we've known the radius of the atom. And we can use them to interrelate the two so we can relate the size of an atom with the density of the metal. Now, in this particular one, as we saw earlier, there's a gap here that we don't know the length of. And so we can't connect L with R using these two atoms. And then additionally, we have to go in and then back out to connect these two atoms. So neither of those is really beneficial to us to give us a simple calculation. The one time that it works is to go from one corner of the cube to the complete opposite corner. So from the top left to the bottom right, you will go through the center atom. There will be constant contact from this atom to this atom to this atom. Now, let's call this atom 1, let's call this the central atom, and then this atom 2. So what we'd have there is we'd have the radius of atom 1, we would have 2 times the radius of the central atom, or the diameter of the central atom. And then we would have 1 radius of the second atom. Now, if all of those atoms are the same atom, in the case of a metal, that adds up to 4 times the radius of the metal. What we can do with that is we can set up a little bit of trigonometry to be able to connect the radius with the side length. And to do that, what we're going to do is we're going to look at the length of this part of the cube, the diagonal that goes across the bottom face. So what we end up there is we end up with a right triangle where this side is 4R. This is our diagonal that goes all the way across the cube. This is our diagonal that goes along the bottom face as I'm drawing it here. And then this is our side length. So this is just literally the distance between these two atoms. So we would call this our side length. Now the bottom diagonal can be thought of as its own right triangle where let's call this atom 3, this atom 4, and this is atom 2. So we're looking from 3 to 2, but from 3 to 4 is L, from 4 to 2 is L. So therefore we have a 45, 45, 90 right triangle. So L squared plus L squared equals the hypotenuse squared. Therefore the hypotenuse is square root of 2 times L. So we can go back now and we can set up this triangle, square root of 2 times L, and we can relate what L is with what R is. So our equation for that is going to look as follows. We're going to have L squared plus square root of 2 L squared equals 4R squared. Don't forget to square the 4. So we have square root of 2 squared is 2L squared. So we end up with 3L squared here equal to 16R squared. So we can now relate L with R. So if we want to know what L is going to be equal to the square root of 16 over 3 times R. square root of 3 over 16 times L. Okay. Now, that's going to give us information about the volume of the cell or the size of the atom. There's one more important thing, though, to note in this cube, and that is that there's one central atom. That central atom is just going to belong to this unit cell and this unit cell alone. So we get to count this as one atom for the unit cell. There are also 8 corner atoms, and those are shared between other unit cells. Now keep in mind, this does not exist in isolation. This is a massive crystal that moves in all 3 directions. And so we have another one here, and another one here, and another one here. This corner piece here is shared by 4 unit cells beneath it and 4 above it. So 8 total unit cells. And so only 1/8 of each atom will be counted towards this, so that we don't count things twice. So each corner atoms actually only count 1/8 of each, so we end up with 1 atom from those 8, and we end up with 1 in the center. So whatever our metal is, in this unit cell, we can count 2 atoms worth of that metal. And that's going to be information that's going to be able to provide us the mass of the unit cell that we can use to couple with this to figure out the volume of the unit cell. Now, let's go ahead and look at face center cubic. So face center cubic is probably a little bit easier to visualize. Let's start with our cube again. All right, so again, we're going to have our 8 corners. Now for face center cubic, we're going to have 6 more atoms, 1 on each face. So on this front face, we're going to put 1. On this face, we're going to put 1. Back, 1 back here. Front over here, the bottom, and the top. So we have 6 of these blue atoms, 1 at each face, and that ends up looking like this in 3D. We have a little model here. So any face you look at, you have your 4 corners that you can see, and then you have the 1 face that's in the middle of them. So as we rotate that, careful not to break this, that's what we're seeing. Now for the contact here, there's a gap that's of different sizes depending on the relative size of these things, but there's a gap between the 2 corners. So to get constant contact, you're going to go from one corner to the face atom to the other corner. So you're going to kind of create a diagonal. Now, let's draw that like this. So if we're looking at a face, we have our center, and then we have one corner, one corner, one corner, one corner. So what I'm saying is that our constant contact between atoms is this diagonal across the face. So if we label this, let's call this atom 1, 2, 3, 4. Here's 1, 2, 3, 4. So from atoms 1 to 4, or from 2 to 3 really, that's where we get our full diagonal that works with all the atoms are touching. In between 3 and 4, and 1 and 3, and 1 and 2, we have these gaps. Okay, so how can we use that? So what we have here is we have 2 radius, or whatever the white atom is, and we have 2 radius, or radii, of the central atom. So it's diagonal. So total, we have 4 times the radius of whatever this atom is, if it's the same atom for each one. Okay. Well, from our trig then, we also have, this is the side length, and this is the side length. So here is a little simpler. We have 4r is equivalent to L squared plus L squared, like this. Okay, so we're going to end up with 16r squared is equal to 2L squared. And so solving here, we're going to have r is equal to 1 over 8 square rooted times L. And then L is going to be equal to square root of 8 times r. Okay, as far as analyzing how many different things are in here, we have our 8 corner pieces. So 1/8 of each of those counts towards this unit cell. That's 1 atom we count towards the unit cell. And then our faces, how many cubes are those shared between? So the face is just 2 cubes in contact with one another. So we have 6 face atoms, and then each one of those is shared with 1 other unit cell. So we're going to count half of this atom towards this unit cell and half towards this one. Half of this one towards this one, half towards this one. So when we're done, we're going to count that as 3 total atoms. And so we'll have 4 total atoms in this face center cubic model. Okay? So we can use that for density calculations as well. Let's summarize those counting atoms for a second. So if you have a corner, you're going to count 1/8 of that atom. So usually you'll have 8 corners in a cube, you'll end up with 1 atom from that. For a face, you're going to count that as 1/2 of that atom towards that unit cell. For a side, meaning here's your cube. So if you have one that's on the side, that's going to be shared with 4 other cubes. So this is shared with this cube, 1 here, and 1 back here. So that will count towards 1/4 of that atom towards the unit cell. And then a body means internal to this cubic structure, so not along the lengths at all, so it's not shared by anything. So that entire atom will count towards that particular thing. Now let me show you a sample question where this gets a little more complicated besides face-centered cubic or body-centered cubic or anything like that. So this is a question from a chemistry Olympiad test in the past. So here we have a whole bunch of different atoms. We have atom A is this one that's in the middle of the cube. So A counts as 1 single atom towards the unit cell. And then for B, we have these dark sphere or circles over here, spheres, and they're at the corners. We have 8 at the corners. Each one only counts for an 8. So B only counts for 1 atom applied towards the unit cell. Now for C, we have these kind of white or clear or whatever they are, spheres and those. Those are along the side lengths. So we have 1 on each side. We have 4 here, 4 in the center, 1, 2, 3, 4, and then 4 at the bottom. So we have 12 total for C. However, only 1/4 of each of these counts towards this unit cell because this is shared with 4 other unit cells. So we have 1A, 1B, and 3 C's per unit cell. And so we end up with B as our answer, ABC3. That's what the empirical formula of that particular substance would be. Okay, taking that out to make it a little more challenging, we can now do density calculations. So here's a sample problem where we have aluminum, it gives us the density, and it gives us the arrangement face-centered cubic. Determine the radius of the metal in picometers. Okay, so we're in grams and centimeters cubed. So the way we want to do this is this. Face-centered cubic, let's start with a picture of our, and just to kind of get warmed up here. So let's get our cube. Okay, so face-centered cubic, we're going to have 1 on each face. We're going to have our 8 corners. And for face-centered cubic, let's go ahead and put blue, 1, 2, 3, 4, 5, and the bottom 6. So for face-centered cubic, how many atoms do we have? So we have 4 aluminum atoms. 1 from the corners and 3 from the shared faces. Okay? So we want to know 2 things here. We know the density, 2.70 grams per centimeter cubed. And because we know there are 4 aluminum atoms in this unit cell, we can figure out the mass of 4 aluminum atoms. So 4 aluminum atoms is going to be the molar mass of aluminum divided by Avogadro's number times 4. So this comes out to be 1.79 times 10 to the negative 22nd grams of aluminum per unit cell. So this is the mass, the molar mass of aluminum divided by Avogadro's number times 4 for the 4 atoms. So a very small mass. And we can couple that with the density to figure out the volume. So the volume is going to be equal to the density divided by the mass. So 2.70, oops, let me get that upside down. Yep. Mass divided by the density, sorry. Yep. So we have this 1.79 times 10 to the 22nd, negative 22nd, grams, divided by the density of aluminum, 2.70 grams per centimeter cubed. So our volume ends up being 6.64 times 10 to the negative 23rd centimeters cubed. And that's our volume of our cube. So the volume of the cube is equal to length cube, so we can find our length from that. And our length is 4.05 times 10 to the negative 8 centimeters. Okay, so now we want to go through and we want to figure out what's the radius. So for our face center cubic rate, keep in mind that we're looking at this diagonal across the face. It looks like this. So we know the length here is essentially 405 picometers. It's from here to here and from here to here. So we want to know what this is. Now this is 4 times the radius. So we're going to have 4 times the radius squared is equal to the length squared plus the length squared. So 2 times 405 picometers quantity squared. Nope, just kidding. Squared times 2. So we have L squared plus L squared. So 2L squared. Okay, so when we go ahead and solve this then, what we end up with is 143 picometers is equal to our radius. So then that would be 1.43 angstroms, the radius of that particular atom.